so broadly we'll talk about the deep generative models, but before we do, this is what we do at NeuroPixel, right? So all the images that you see here, apart from the apparel, everything is generated. The model is generated, the background is generated, the entire immersion is also generated, right? You can go to NeuroPixel.AI, our website, and understand what we do. We are very verticalized in kind of building stack in deep generative models, computer vision for fashion e-commerce platform, right? Now, this talk is primarily on the kind of journey of deep generative models. And yeah, so that's all it is. So if you see the problem, right? So the problem is, what is the problem of generative models? I'll broadly speak from the computer vision because that's what we do, but the same thing applies for other signals as well. So you see observer data, of course, which is x1 to xn, IIDs, independence and identical distribution, and coming from like, so it will be r to the power d dimension. So, but I do not know what that distribution is. I just have observation from the distribution, right? And I want to two things, right? One is I want to estimate px, and second is I want to learn to sample from px. The first one is a very hard problem, actually. And the second one somehow is tractable. And that's what we do in deep generative models, right? Now, classically, there is something called Gaussian Mixture Model, okay, GMM. Now, what is it? It primarily is basically say that any distribution you can see as a combination of some Gaussian mixture, right? So each of these distributions are a Gaussian distribution with, let's say, mean as mu I, and of course they have a covariance matrix, which is sigma I, and their ratios are pi i's, which is basically if you have G distribution, so summation of pi I Gi is 1, right? Assumption is like pi I is greater than 0, of course. Now if you do that, and then your problem comes down to this. So this is your maximum likelihood estimation, which is theta star MLE, would be argmin of, this is our KL divergence, okay, Fy and F theta y. So Fy is our actual distribution, F theta y is what you want to kind of achieve, and this, I mean, KL divergence should be minimized, okay? That's the problem, right? Now, it also boils down to, if you do it further, because these are Gaussians, so you can see that, it can be shown that this will be similar as maximization of the log likelihood, okay? Because these are Gaussian distributions. So if you take the log and on, and log being a continuously increasing function, you can show that, okay? And the problem with this is, this is the theoretical approach, right? And you basically try to find out all the mu's and kind of your variance covariance matrix. The problem is here is very difficult, and I'm talking about very large kind of dimension, like basically as an image, if you have a 1024, this is 1024 cross 1024, that's the dimension, right? It's very, very difficult to parameterize this kind of very complex distribution. So to get a parametric solution, which is basically, I mean, getting that mu's and those variance covariance matrix is very, very hard. So now here actually deep learning comes to help. Okay, now what you do is we try to parameterize F theta y using DNN. Now what is our backbone? Our backbone is, so there is something called universal approximation theorem, which basically gives us a theoretical confidence that if this is more than, more than multiple layers, like more than one layer actually, if it is one layer, then any kind of bounded function can be approximated to a significantly high degree of approximation using neural net. And if it is more than one layer, if it is multi-layers, then any non-bounded function also could be approximated, right? So that's what neural nets is called a kind of universal approximation. So the whole idea is you approximate this F theta y kind of using a deep neural net, okay? Okay. And now we'll talk about something called evidence lower bound, okay? Now here, we see this log of px, right? If you go back, so this is what I wanted, right? This is what this log of fy, right? Now, if I come here, so this is my log of px. Now that basically you can do a px j dz. So this is your kind of joint distribution, basically marginal distribution, and over dz, and then you do that, and you have your base theory, then you apply that, and you can see this is log of expectation with q phi z given x and this, right? Now there is something called Jensen's inequality, which basically gives us that this should be greater than expectation of log of this, which is basically g of expectation of this function is greater or equals to expectation of g of this function for a concave function. Now what is concave function? Kind of a log function where you have this point, so each and every, if you connect 2 points, it will kind of lie behind the curve, okay? So g of x plus 1 minus alpha, like g of alpha x plus 1 minus alpha y would be less or greater or equals to g of alpha x plus g of alpha 1 minus x. So from that this comes, this is called Jensen's inequality. So if I want to maximize this is my lower bound, correct? Because this is always going to be more than this, right? So this is called evidence lower bound. The another way to look into this is the same way. You can do a log of px, then you do this is actually 1 by the definition of probability, and you do that, and you basically you keep on doing that, and you can show, so this is this plus dkl, that Kullback level, KL divergence of q phi z given x and p z given x, right? Now this KL divergence is always greater than 1, okay? This comes from something called Gibbs inequality. Basically from entropy of any kind of distribution is always greater than the cross entropy. So basically px log of px integration of this is greater or equals to px log of qx, right? So that's called Gibbs inequality. And from Gibbs inequality, we can say that this is always greater than 1. So then therefore this term is always greater than this. So these are the same way. Now what we try to do is any DGM in order to maximize this, because maximizing this, if you remember, that's the problem, right? What we do is we try to maximize this term, okay? This is maximization of elbow. So this is the variational autoencoder, okay? So what we do is, so it's the same way, if you see, so I have a latent space which is Z. I try to kind of have a this is my encoder actually. So this is q z given x, and this is my decoder from z given, x given z, right? And if I do that, so I see there are 2 terms, okay? I have this term, okay, log of x given z, and I have this term also, which is KL divergence of this, okay? Now what I want to do is, if I want to maximize this is my elbow, remember? So if I want to maximize this, I want to maximize this, and I want to minimize this, correct? So I can minimize this, which is basically the PG, whatever I do not know what is it. However, by q phi z given x. Now, this is called the prior matching term, okay? And this is very, very important. I will come to that why VAE is so important and all in the entire journey of DGM, okay? Now, this is the prior matching term, and this is called the reconstruction term, okay? What is this? From the z, if I want to sample, how close I can come to actual distribution of x, okay? So, before that, if I go here, So there are 2 things happens here, okay? I want to maximize this and I want to minimize this, okay? Now, in order to minimize this PZ and all, right, I can take any theoretical distribution and all, right? What normally we take is basically again a Gaussian distribution with a variance covariance with basically only the diagonals exist. That means there is no interaction between those dimensions, and this is very important, so that we can achieve kind of minimal level of entanglement, okay, theoretically. However, the moment I will go there, I have to compromise on my reconstruction term, okay? So my reconstruction might not be very accurate, however, it will be very disentangled. Because what happens is, if you want to modify one attribute, you normally see the other attributes getting affected, okay? That's called entanglement, right? Okay, so it's not like if you're going into one direction, it's not that you are actually shifting to some other, so you have x and y, and you want to move only through x, you always see there is a shift is happening in the y direction as well. That's called entanglement. But with this kind of design, you can achieve that theoretically by making that, forcing this PZ to be a Gaussian and all, where variance covariance matrix as a diagonal one. That means ideally that there is no covariance apart from the variance. So that means that you can force it to follow certain kind of Gaussian distribution. That means you can theoretically achieve zero entanglement. However, this reconstruction would slightly get compromised, okay? This is called the reparameterization trick. This is basically we do in order to kind of have a differentiation and all, because you do a random sampling from Z, which is very difficult to do a differentiation. And that's what you would basically write this as a kind of mu phi x plus sigma phi x dot epsilon, where epsilon comes from a Gaussian epsilon 0, 1. This is random noise. That's normally the architecture of VAE. And that's normally the architecture of VAE. So you have, So you have, the up one is actually a simple encoder and decoder, but however, the below one is actually a VAE where you are having Z in terms of both mu and sigma, and so that if you can see, this is the actually kind of from where, this is your latent space from where you are sampling, once the training is done, okay? Once the training is done, then there is no encoder, you just decode, okay? Now you think about this, so you can have these multiple layers also, right? So you have like, you start from these, then you have Z1, then you have Z2, then you have Z3 and all, then finally you have ZT, and then you started decoding and all, and then you reached again next, right? So if you have that, this is called hierarchical VAE. Okay, hierarchical VAE is better because in terms of improvement than normal VAE. It helps in the reconstruction, etc., etc. Now, what is Markovian? Now, Markovian is basically where we say the distribution of, let's say, this Z1 or any particular Z at t time only depends on t minus 1 and anything else. Okay, that's Markovian. That's actually the definition of Markovian process. So now if I have a HVAE, okay, and which is, of course, this is the chain, but I also say this is the Markovian process. So I don't need to worry about the prior state, I just worry about the immediate prior state. Okay? Or as you say, the future only depends on the present and nothing else. You can think of both ways, okay? Sorry. Yeah. Correct. Now, if you, so if you see a little bit of here, there, you can see, so this should be your kind of, this will naturally come. Then again here, this is your log of px. Now this time it would be only kind of j, because you have t state, right? So it's not only single one state, so you have 1 is to t, 1 to t. This is basically 1 to t. Given x and all, and this becomes your kind of elbow. And then that's what you want to actually again maximize, and that this should be your kind of modified elbow, okay? Now this is what we do actually in the diffusion and all, okay? This is a very, very initial work on VDM, okay? Also known as DDPM, denoising diffusion probabilistic model. What we do here is, we say this is also an image VAE, however, this Q xt given xt minus 1 is just a Gaussian of, what is it? It just comes from the earlier state. So basically it depends, its mu depends on this earlier state. So this is a Gaussian with some constant, which is, let's say, alpha of xt, and with some variance covariance function. So that's all it is, right? So it's basically Latent dimension, and these all the dimensions are same. Okay, there is no change in the dimension. The structure of this vehicle is not learned. It's always like, it's basically, I know that's a linear Gaussian function, and this Latent encodes over very time, with the distribution of Latent final sum t at the standard Gaussian. So this will be a standard Gaussian. That means Gaussian 0, 1. Okay? Yeah. So this is basically the model is, okay? Now what is it? This is very important part, this one. Okay, so Q xt given xt minus 1, if you go back, this is Q, right? How basically I'm from the signal, I'm getting complete noise. This is my forward. And my backward is from the noise to actual signal, correct? Now this is what it is. So root over of alpha t, xt minus 1 and 1 minus alpha t I. I is basically variance covariance matrix, where all the diagonal elements are 1 and the cross diagonal elements are 0. That's what. Now, if you see the alpha is high, that means this is very simple, so less noise, and alpha is high means this is less. That means there is less variance, but it is almost similar to xt minus 1, the mean of that, right? So that means this is very less noise, and if alpha is more, that means alpha is less, that means more noise. So mu is slightly kind of, this is less, but this is, variance is high, that means more noise, okay? Okay, now, and you can also, this is very straightforward. If you run 1 to 2 given x0, so you can achieve this. This is nothing, is basically you just kind of, because just a Markovian process, you just multiply all the probabilistic distribution. Same for x0 to x3 also, the same thing will come, okay? Now, interestingly, so that this is basically this backward process you try to kind of parameterize using help of a neural network. That's what this, you can see this is, I've mentioned this as a theta, because here the parameterization would happen. That means that I'll try to model this using a neural net. Okay. Now, if you see here, now from x0, I'm going to xt. Now, if I solve this, log of px is this is my elbow. Now, of course, there are a lot of other steps, and of course, I jumped it. But this is the important part. This is the reconstruction term. That means how good I am from x1 to x0. This is my final x0. That's what I want to achieve, right? This is my reconstruction term. I want to maximize this, of course. This is the prior matching term. So basically, the last step, it should be p of xt. But I know p of xt is Gaussian 0, 1. So I know there is not much of learning here. And I know there is no learnable parameter here also, right? So this is fine. This is very interesting. This is what I want to actually achieve, right? So I want to minimize this scale divergence. This is called consistency term. So that means when I go through from signal to noise, this is my qxt given xt minus 1. And when I come from noise to signal, that means p of xt given xt plus 1. This kind of distribution, difference of distribution to be minimized. This is called the consistency term. However, so this is clear, right? This is where I will try to minimize this, right? Okay? Now these two terms are pretty straightforward. Now that's why this is called consistency. Now interestingly, this has two terms. If you see xt minus 1 and xt plus 1, there are two random variables here. So now, which is not very what can I say, because it's not very easy to kind of do this using a kind of MCMC, basically Monte Carlo simulation, to get to this because of two random variables, and normally you will reach kind of a suboptimal. So because it's always easy to kind of do it with one random variable. So that's what we try here is, we do this. Okay, of course, there are a lot of derivations and nothing much, just derivation. But what we achieve is these two terms remain same. Only this, if you see here, it becomes xt minus 1 given xt and x0, p theta xt minus 1 xt. So now this denoising matching term. So now the denoising matching. So basically, it basically says, like if I qxt minus 1 given xt and x0, of course that's my prior. There is a liberty. There is another pink line should go from x0 to actually this, which I have ignored. So that should match this actual denoising term which I'm trying to do, right? So this is basically the theoretical denoising, right? That's the basically Q distribution. Now if I want to come from this to this, that's my distribution, okay? So Q xt minus 1 given xt and x0, and this is p theta xt minus 1 given xt, right? Right? Okay. You can do a little bit more math, so you can show that so this is q xt given x0. Now, if you remember, I said that this comes from alpha xt minus 1, right? This was the earlier assumption. Now, if you continue doing that, you could show that xt can be shown as a kind of a Gaussian distribution with mu as this and kind of sigma as this, okay? So from that you can show, again, so this is from the base theorem, you can rewrite this as this, and then you can show this q xt minus 1 given xt and x0 would be again a Gaussian distribution, of course, xt minus 1, with this as your kind of mu q, xt x0, okay, and this as your sigma q, okay. This is very important. I'll come to this again and again. Now, if you see here, okay, so this is your KL divergence. Now you do it, again there are a lot of steps and all. You can show that this is your minimization of mu theta. Mu theta is actually what you try to, this is your parameterized one, this is the actual one, and where mu theta is this, and mu q is kind of this, right? You can show from here that this is your x theta hat, which you have actually kind of estimated, and x0 is actually what is your original one, right? So you can think about this, that all your these models and all, you can think, if you think, yeah, here, that it's basically from any state, right? If I want to go back to x0, how close I am, that I want to minimize. And that could be from any path, correct? And from here, right, from any of the state, right, t minus 1, t plus 1, any state, you want to go back to x0, okay? And that's what it is, okay? Any xt, right? That's what it is. And you want to go back and you want to see like how close you are, and this is your kind of minimization function. That's what you want to minimize. This is your pure signal and all, right? Okay. There is another way of looking into this. You can show a little bit this thing that it is also kind of minimizing this signal to noise ratio, we say. Okay. Okay. I have 10 minutes. I'll finish it. So this is signal to noise ratio. Okay, and that's broadly it is. So if you can, how do you sample the noise? So you can have a decaying function and all, which is basically e to the power minus omega, nt, and this n also again you can parameterize with a neural net. Okay. Yeah. Now, if you go a little bit of more kind of do a little bit of more kind of manipulation and all, you can also show that this is similar to basically estimate the initial noise, of course, which is Gaussian 0, 1, from the noise at state t, which is basically equivalent to kind of have a signal xt and then kind of, let's say signal xt, and to go to x0 is similar to get the noise at that particular time step t and go back to the initial signal, initial noise, which is epsilon 0. Okay? You can also show this in a very similar way, that this should come as this is we call a score function. Okay, score function is nothing; it's basically a grad of x. So this is grad x. Okay, so basically you try to kind of understand which direction you need to move in the data space in order to maximize the likelihood. So that's called the grad of x. This is called the score function. It is also similar to minimize this kind of. You estimate the score function again using a neural net. So this is your neural net part. And you want to minimize this. It is exactly same as the original kind of how can you minimize the actual score, kind of how close you can estimate the score function. That is basically the same kind of interpretation. So you can either there are three ways, right? You can have that xt to go back to x0, you can have the epsilon t to go back to epsilon 0, or you can kind of model the score function as good as you can do, right, at any particular timestamp t. So score function, so this is the broadly what the definition of score function. It only happens for the kind of, if you have a, we call it as an energy model, which is basically of this form, e to the power minus f theta of x, which Gaussian also is a, comes under this energy, this thing. Why do you do is because this has this kind of this 1 by z theta, which is very difficult to handle, analytically. So we just get rid of this z theta using taking log, and if we do a grad x with respect to that, we completely, if you see that, grad x of this is basically grad x of f theta x. So you don't need that, right? You just f theta x. And then you come back to this, right? So that is the reasons we do that. This is actually the physical definition of the score function. What we try to do is you start at any point, and then, so this, by this, okay, with this function, you try to get into any of the mode. Okay, these are your actually data mode and all, where you have the maximum probability of the data distribution. So this is where you want to achieve. This is where you want to grow. Okay, this is where you want to go. Once you achieve this, then you can sample from here. Okay, that's what happens. Okay, so that's what. So this is broadly Langevin dynamics. Yeah, and you can also show this is similar, and basically you can add Gaussian noise to a particular signal, and then once you do that, and then you can do this kind of follow this procedure in order to reach to this mode and all. Okay, that's all it is. It also can be shown. This is broadly same as a kind of stochastic differential equation, and then the reverse process become a reverse reverse SD, and then you sample using this. Okay. This is exactly what we do at stable diffusion. So what is this? This is basically the initial signal. Then you have an encoder. This is your latent space. Okay. Now, then you have a diffusion process. Now, why do you call it latent diffusion? Because entire diffusion happens in the latent space. Okay. It's very difficult to do it in a very large, like 1024 cross 1024 kind of data space, right? So we just do it in a much smaller this thing in the latent space, and then of course use a decoder. I'll come to this. So this is your kind of diffusion process, and then this becomes your denoising process. Okay. And these are your conditional generation. Okay, these are your conditional generation. So all these kind of, you can give anything, you can give text, you can give image, these are all your conditional generation, okay? So all these things remain same, it's just like P of xt given y at certain this thing, right? So these are your y's. Now this you again go through a kind of encoder, and then this is your transformer. Okay, this is called in stable diffusion they call it Vision transformer, and then that of course Q and K dot product by V, and then you kind of do the denoising process for step T. That's what you repeat this T times, and then you have the final Z, and then you have a kind of decoder, and then you reach X as, and you try to kind of match this. That's the dot process is. Once the learning is done, you just cut it. You just have kind of this path, okay, not the upper path. That's all. So that's broadly what we do. So all the companies who like us and NeuroPixel and all, what we primarily try to do is basically have this latent manipulation, okay, this latent space manipulation with the help of this conditional generation. Basically, how can I condition the light map, which we have done, like so that it looks very immersive. How can I change this kind of hair? How can I change the skin tone? I mean, all those stuff. How can I change the posture, etc., etc. Yeah, that's broadly it is. Yeah, okay. Questions?